Welcome, everybody. We'll start in a couple of minutes. There are still people dropping in, so a couple of minutes more. Thank you. Ska tillbaka hit så.
Ska vi starta? Yeah. Okay. Welcome everyone. I see there's more than 50 people online to attend and listen to this inaugural lecture by Pallarès. Just a brief introduction of David for those who don't know him. He took his PhD in 2008 in this department, also on the topic of a fluidized bed. And before that, he has been studying in Spain, Barcelona. And after his PhD, he has more or less stayed at Chalmers all the time, as far as I can see from his very extensive CV, apart from 2 interesting jobs as Inspector of Environmental Impact for the Catalan government and Advisor on Energy Investments in the Caribbean. So maybe we will hear more about that later, David.
Tonight.
What more can I say? He was proposed for professorship in last autumn and examined by the internal body of the department. It went straight through there and it went to the central committee, ARCO committee, and we received his evaluation, which was very clear. I'll come back to those afterwards. And as a result of the evaluation, we are here today and we'll hear his final lecture before he hopefully becomes a professor, the inside of fluidized beds and its role in sustainable energy conversion. David, the floor is yours.
Thank you very much for this nice introduction. And as our head of department said, the title of this lecture is The Inside of Fluidized Bed and its role in sustainable energy conversion. But before we dip into the topic, I would like to share with you what is my vision, mission, and backpack. As you see, I have been attending leadership courses. And I would say my vision is a world fueled by sustainable energy systems. And the mission inside me, in order to get there, is to attain a level of knowledge of the flows in fluidized bed units, which is enough, which is able to make possible the efficient development of new applications. And last but not least, what do I have in my backpack to achieve this? Well, it's the development of validated generic descriptions for large-scale fluidized bed combustion. And as you can see in this picture, I'm not alone. I have not been alone in my journey, and I hope I will not be in the future in the path to the summit, so to say. And in my backpack, I have worked with different pieces of fluidized bed combustion, both experimental work and modeling work. And I know that when I reach the summit, so to say, when my mission is complete, it's not enough that I complete my mission. I mean, in order to attain this vision, there must be a lot of people in the summit with other missions coming together. The point is that when this happens, I want to be up there with those people too. So the lecture is divided into 3 sections. I'll first talk about the inside of fluidized beds, the physics inside the reactors and some key aspects. It's a bit of a crash course into fluidized bed reactors. Second section is the outsides, where these reactors can be put in different processes and how do they interact, what's their role in those different processes, and what are the key question marks. And finally, I will have a section discussing the mining of new knowledge. How do we develop knowledge? How we attain new knowledge in the field of fluidized bed technology? So let's go with the beginning, the inside of fluidized beds. And as I said, this is a crash course. So this is the ABC of fluidized bed technology. Their function is primarily to allow gas-solid chemical reactions. And here the orthodox people will say yes, but there are gas-solids-liquid fluidized beds. Yes, there are. And there are beds which are not intended for chemical reactions, but for physical processes like dryers, heat exchangers. Yes, they are. But I would claim most of them, those applications are for gas-solids chemical reactions. So key aspects, I will walk you through these 3. And finally, we'll look at the 2 main types of fluidized beds. Yes, I will offer you some, if this allows, of course, which maybe it does not. No, I was thinking of sharing some video with you, but it was not possible at this time. Let's continue. First key aspect, the gas-solids contact. Well, one thing that one has to keep in mind is that the gas flow is divided into several phases, and just at a certain time, at a given time, it's only a tiny share of the gas which is in contact with the solids. We did some study on this, which combined experiments, digital image analysis, and CFD modeling in order to see the streamlines of these gas. And as you can see, we could see what time they spend in the emulsion with the solids, how much time they spend in the bubbles, and so on. And one could extract statistics of this and some conclusions. And we found that a way to describe it is to say that, yes, it goes into 3 phases, the emulsion phase, the bubbles, as you can see, and then some shard cutting jets. Sometimes the bed opens itself totally, and then the gas will live without any whatsoever contact with the solids. And only the ones in the emulsion will have the chance to be in contact, depending on the mass transfer, how good that is, but will have this chance to be in contact with the solids. So all in all, which share of the gas has come into contact with the solid surface will depend on a lot of parameters, will depend on these exchanges between phases. And it turns a quite complex question that we have been and we will continue to look at. But still, there is a question mark on this, how to describe this efficiently. We have also another aspect is the one of solids mixing compared to, for example, PC boilers, burners, in which you force the reactants to meet at a certain location or to enter the reactor at a certain location. Here we have the solids typically in a point feeding somewhere from the side of the reactor, while the gas is distributed feeding from the bottom. And then, of course, there is a challenge here in making them meet. So the lateral spreading here has to be fast enough to ensure that there is a good contact between gas and solids. We have been studying this too. We can see, for example, this is from the, and now you will excuse me, I will fix this once and for all. Yeah, now it should work. So this is the Chalmers gasifier from the roof. And what we will see is that we throw in some phosphorescent fuel particles and we turn down the light. And then with this, we can do digital image analysis. And it looks like this then, this lateral spreading. And as you see, we have lots of concentration here, but of course, there is some lack on the other side. That is the challenge that we need to meet then. From this, we can get statistics and so on, but still we want generic descriptions of this. This is for a specific unit at specific conditions with specific solids. What we would like, what is our goal here is to have generic descriptions of this. So again, a question mark here. Another one is the gas mixing. So sometimes the gas that we are injecting is to react with the solids, but also with some gas which is internally produced in the reactor. This is an example of this is the volatiles generated in solid fuel combustion. We have this video from Twente, and here these flames that you can see here, it means that the gas that we're injecting, air, is meeting the volatiles released by these fuel particles. And then you can see these flames. And apparently one would say this is good. There is a good contact because we see a lot of flames. But those who are alert can see once in a while here dark smoke coming up also. And that gives an indication of that maybe the whole picture is not that perfect. There are measurements from the Chalmers boiler here. And what we can see is that measuring the fluctuations between reducing oxidizing conditions, that we still have quite much presence of volatiles. And of course, this volatile concentration decreases with height. But what we see is a fluctuation in the gas concentration. So this tells us that there is also a non-perfect mixing of the gas on the time domain. Finally, another property important to know about fluidized beds is that of thermal inertia. And I want to give you this example. So if we have a tube reactor with oxygen and at some point we inject hydrogen, then we will have, of course, combustion and a release of heat. This will increase the temperature. And then if we cool it down, it will decrease the temperature. If we extract the same heat that has been released, it will go back to the same temperature. Now the question is what happens when we have solids in this picture, when we do not only inject oxygen, but also a flow of solid particles. There is a lot of mass in this, much more than in the oxygen. And what this will create is a thermal inertia, and this will dampen both the temperature increase and also the decrease because of this thermal inertia. And this is a known property then of fluidized beds where there is a lot of solids mix and solids flow, that you have rather homogeneous temperature fields. And finally, we come to the different types of fluidized bed units. And if we start with the bubbling case, which is the typical that we are used to, I would say, we have here a certain cross-section, and then we want to increase the capacity of our unit, of our reactor. Well, we do that by increasing the cross-section. We keep the same velocity, so with an increased gas flow, we need to increase the cross-section, and then we will grow until a certain critical size. And this size becomes critical because of cost or performance, mixing, and so on. At this point, what we need to do is if we want to continue increasing capacity, we want to put then more gas flow into this. But if we cannot increase inside, then we go down inside. And going down inside, but increasing the gas flow makes the solids start to circulate. The gas flow is high enough to start dragging up the solids. This means that we will need a system to recirculate them. And here we have then the circulating fluidized bed. Okay. If we then keep the scaling up, we will again come to larger sizes, of course. But this is the main background to why we have these two different types of units. Yes, and finally, this was the first section. We have gone through the function key filters and the types of fluidized bed technology. And now I can give you this hypnotic video that you could look at for ages, I guess. This was, as I said, first section. Now we move on to the second one, the outsides. And I will begin this section by giving a bit of some historical perspective. The whole story starts 100 years ago in Germany. With the Winkler gasifier. There is a patent on that, and that's for gasification. And gasification has been in the picture quite much the whole time, I would say. This is a very beneficial technology especially for embargoes and wars, when you don't have access to say, oil or gas, then you can produce it by gasification from solid fuels. So it has been there the whole time. In 1937, Exxon invented the cracking process for crude oil. And since then, we have had a lot of fluidized beds dedicated to this. And this was the time of oil. But in the 70s came the two oil crises, and then a fluidized bed turning the ice towards coal combustion. At this very same time, 81, we had our 16 megawatt BFB bubbling combustor at Chalmers installed. You can see the picture here. And 89, we had a circulating fluidized bed installed, 12 megawatt. And this unit has given a lot of joy and publications and data and knowledge to the community, the fluidized bed community. 91, we have the CO2 tax in Sweden, and this is to combat the pollutant effects of coal. And since then, we have seen a large increase in biomass combustion, in fluidized bed biomass combustion. And what we have now in this century, in this millennium, is the awareness for climate change, sustainability, and this has opened then for CO2 markets and cost-efficient renewables. And 2007, in this new period, so to say, we had at Chalmers this 4 megawatt indirect gasifier. What I see in the future then is that these technologies some of them will still be there, but we need new fluidized bed technologies that tackle carbon capture and storage, more complex bioenergy conversion, energy storage, pollution generation, recycling. And maybe I would say one of the most important highlights in the story of fluidization was in 98. There was this master thesis student coming to Chalmers, and he did a master thesis that still the world hasn't witnessed anything like that again. I would like, again, to focus here. Most of fluidized bed devoted in the energy field is been in combustion. And I want to show you these statistics. It's from the IEA report. And what we see is a clear stagnation, I would say, of fluidized beds. So we have the innovation periods, then we have commercialization clearly, and then we have maturity. And you see it is saturating, stabilizing in most of the world. It's only clearly Asia, but not China or India, where it is increasing. This is Malaysia, Indonesia. But otherwise, in the rest of the world, it seems to have reached some kind of maximum capacity. If we look at the fuels that they are using, we have mainly coal here. And then after that, we have biomass. And this is quite tricky. This is a logarithmic scale on the y-axis. So here the factor is more than 10. We have 30 gigawatts, thermal gigawatts for biomass and about 400 for coal. And if we compare this to Europe, these are global numbers, but if we compare to Europe, we see also big contrasts. In Northern Europe, we have most of it as renewable fuel, while if we go, you can see here just a few percent anecdotic coal. But if we go to Eastern Europe, then we'll see that it's 80% coal. So if you make the numbers, it's actually Canada, some of the US, and Northern Europe that stand for this biomass mainly. The rest of the goal is FB, fluidized bed, is a synonym with coal, and this is something you notice in conferences. So this is an interesting point to have in mind also. I can see this as it's one of the big philosophers of last century. The quote reads that the old world is dying and the new world struggles to be born. And I think we are there somewhere. The old world is clearly maybe not dying, but at least saturating or starting to sleep. But the new world is on the way. And you can see that at conferences also, where more and more papers contribution, more and more research is devoted to these new fluidized bed technologies. So we will have a look at those. The first is thermal decomposition. I wanted to talk about just very shortly. So what we have is thermal decomposition of some feedstock, solid feedstock typically. This is endothermic, this needs heat, and this heat is provided by a flow of solids. Experience in this, well, at Chalmers, we have the fluidized bed gasifier. And also, we have been working now in a project together with BioShare with a retrofit of a bubbling bed, this time not a circulating one in Karlstad. So this demonstration plan will be built next summer. Question marks here, yes. How can we ensure a high enough circulation here so that it can sustain these reactions? And how will this feedstock behave inside of it? How will it mix? Because then, depending on how it mixes, it will experience different heat and mass transfer rates. Second type of technologies are carbon capture. We have oxyfuel, where you feed pure oxygen, and then you have a stream which after condensation gives you the CO2 capture directly. And since you inject pure oxygen for the same capacity, you should have a much smaller reactor, but still with the same power. This means that you have not enough area to extract the heat. You do this from the circulating flow. And this is a technology we studied with Valmet, this 4 megawatt unit. And this is the largest unit that has published data on this process in literature for fluidized bed. Question marks here, yes, of course. How will be combustion affected by this high oxygen concentrations and this CO2 atmosphere? And again, can we ensure this high circulation of solids? The other one is called second generation carbon capture, that's chemical looping. And the principle is very, very fast that you circulate a metal. This metal will capture oxygen from one reactor, exothermic one, and bring this oxygen and heat to the other one in which you gasify and combust your fuel. This is, Chalmers is a leader in this field. I think there is no doubt about that in terms of running hours and number of papers and so on. So I would say Chalmers has the lead in this field. And there are lots of question marks. Can we ensure such a good circulation as it is required? What is the solids gas contact in both reactors? How will the fuel mix and so on? So again, lots of questions and many times the same questions in the different applications. And finally, I wanted to just give a short insight into the energy storage field. And here what we see is a process in which we have intermittent input of energy. This can be concentrated solar power. This can be valley prices, electricity in the valley prices. And then what we do is that we have a gas solid reaction, which is endothermic, and that we sustain with this energy input. Once this has occurred, we can then have these loaded solids at a high energy level, and we can store them at ambient temperature and transport them for their use so that they can discharge and again produce energy, electricity even, because this releases at a very high temperature whenever we need it. So we've been looking at this also. Again, many questions. Is the solids mixing good enough at large scale to ensure that they can welcome, so to say, all this heat? How is the gas solids contact is another big question, but new questions which are particular to these applications is the transient aspect. Here we have intermittent inputs and outputs with strong variations with time. How will a fluidized bed reactor or system deal with this? And of course, the cost. There is not much in literature about this. So we did some study looking at the break-even electricity selling price for different sizes and then different assumptions on what would be the carbon capture income, because you can combine this with carbon capture if you do this with calcium looping, for example. We are collaborating in this with SaltX company, Swedish company. And this was, in short, the outsides. So now we'll dive into the mining of knowledge, of new knowledge, I have to say. And here we have 3 subsections. First, a short reflection, I would say, of specific against generic knowledge and how they interplay. After that, we'll go through the modeling types. What are the principles and applications of the different modeling types? And finally, a short update on new experimental techniques that we are developing here at Chalmers. As I said, we start with the discussion or reflection on particular findings against generic knowledge. So we have this series of FB technologies that are mature, some of them are under development. But the thing is that each of them has own characteristics. We have this figure exemplifying this for major technologies. So we have fluidized bed combustion. This is a mid-sized combustor, 200 megawatts, as you see here. This is the size, about 40 meters tall. This is the Chalmers combustor, 12 megawatt. So you see the difference in size. And then we compare this to a crude oil cracker, a catalytic cracker. And again, you see it's very, very tall, but very, very narrow also. So this is only size and geometry, but we could talk about solids. The solids are very, very different in these different applications also, leading to different types of solids flow. We could talk about the gas, about the pressure, temperature, concentrations, and so on. So the thing is that we have a very, very wide scope of different conditions in the fluidized bed world. And then we can imagine the different fluidized bed applications. And all of them have assigned some funding can be industry, can be public agencies, but yeah, actors which are interested in developing this. And then the question is, can we find descriptions for all of them together? So can we describe the mass momentum and heat flows for all of them? The answer I would say is, yeah, well, yes, these exist, but these theoretical generic formulations are not affordable with today's computer. And I don't think they will be in at least until I retire. And that's what worries me the most. What we have done, when I talk about my backpack in the beginning, is this. I've been developing descriptions for combustion. And then the question is, can we find or can we extend these descriptions so that they are not particular to this application? Can we extend them so that they also could describe energy storage, for example, or chemical looping, for example? What is needed for that? I think this is a very important topic, and I see many times people trying to use correlations from one application to another and so on. And I think caution should be taken. Just a few punchlines I want to give about this is that direct knowledge transfer between applications is seldom appropriate. It should not be done without being sure of it. Different applications means a wider scope. This means that if we are able to do this, to find formulations which describe several applications at the same time, then the validity is much stronger. It is much more likely that they will also be able to describe new applications. So it's good to have a wide scope when you develop applications and descriptions. And finally, my opinion is that if the fluidization regimes are different, then it's very difficult to actually have any kind of knowledge transfer. That sets, in my eyes, a border which is difficult to actually manage. I will give an example of this generalization of findings. We have here the entrainment of solids from the bottom region of a CFB, and this has been the holy grail, or one of them, in this technology for a long time. And the literature is full of different correlations and studies, experimental studies also. But I would say most of them are unit specific. There are not many who look at different units with different sizes and so on. And the ones that look at different units, they look at the same type of solids or the same temperature. So what we did was to have different units, very, very different in size. Some of them were cold, some of them were at high temperature, about 900 Celsius, and then very, very different solids, again, in size and density. And did these experiments and tried to make sense of it all. And well, what we found at the first sight is when you plot it, it looks like this. You would like to correlate the y-axis to the x-axis, and we couldn't make any sense of it. But of course, looking at the theory, reading, we found then that if you express it in the appropriate dimensionless numbers, then you could find a good formulation for this. And we are very happy with this. But again, this is not a generic formulation for any fluidized bed. There is some limitation on this scope. In this case, it's non-slugging FB solids. So there is always this price to pay, that there is always some limitation when you use this kind of approach. Of course, this is only one example, but there are many more. What is the dispersion? What is the transfer to the walls and so on that we need to look at? So next in the queue is modeling types. And I will start with the modeling in industry and how this has worked through the years. And this was very interesting because talking to the industry, I mean, it has been an incremental development of the technology. You build a bit different and see if it's right or wrong. If it's wrong, you don't do it again and you try something else, so to say. And this is a development, but it goes then rather slow. So when you start doing some kind of models in industry, it most often looks like this, that you have your goal parameter, could be, for example, emissions of CO. And you correlate it to some parameters, some variables. This could be the airflow and fuel flow, or the ratio between these, lambda. You can do that. And then you can find a correlation for this. And use this correlation for boilers, new boilers that you want to design. Until someday, someone tells you that, no, I need a higher boiler, a taller boiler. Well, would you then rely on this correlation? Probably not, because this change in height will represent a change in the residence time of the CO. So then typically what you do is a new set of measurement campaigns, and then you increase your correlation to a 2D correlation and correlate to both lambda and the height. And then you increase your data bank. Good, we're good with that. What happens? Well, as the technology develops, more and more variables are added to this. Different types of fuel, for example, the width of the unit, the secondary air, at what height it is injected, the temperature, and so on. And then in the end, what happens is that the number of inputs has increased that much that you need enormous data banks in order to cover all the possibilities, so to say. Another problem with this is that it's uncertain in the extrapolations. It is rather fine to interpolate, but when you do the upscaling of a process, you are extrapolating. And then it's a bit of a shaky approach. And that's why you don't dare taking big steps, typically. Okay, this is for the probes, but these correlations, it's good because they only take a few seconds or less than that to run in a computer. And they typically are descriptions which are a black box, zero-dimensional, and steady state, so no time or space resolution. It's how it looks in industry, how it has looked for many years. I will talk about this later. On the other end of the scale, we have the modeling in academia, and that's based on theoretical expressions, conservation equations. And here I will just have a crash course into discrete or continuum. If you work late at Chalmers, now when autumn is coming, you will see these birds coming, incredible amounts of them, and flying in a very spectacular way, if you ask me. And here, this is about personality types almost. But if you have people who are very detailed and look at the details, and people who see the whole picture. So if you like details, then you would be a good friend of Lagrange, I guess. It's this guy to the left. If you see the whole picture, then Euler is your friend, I guess. Let me then make or put you a small exercise. I don't want to be the only one making the effort here today. So imagine this square, the yellow one that is marked. And imagine now that we shrink it. And the size of this domain is characterized by this length, L, that we put in the x-axis. And then I want you to imagine or to try to guess what is the concentration of birds as we decrease L, as we shrink this domain. And I will give 15 seconds for this, so you can have some fun today also. Try to think about that.
I should have a prize for the right answer.
Well, there are two answers. But the two of them have something in common. We start here when L is large. As we shrink it, we don't notice any big changes. There are some changes, but hardly noticeable. Because whenever one bird gets out of the domain, it doesn't impact that much. But it will come some point in which a bird in or out makes a big impact. And then we see these big variations. And finally, you will zoom in, well, L tends to 0, you will zoom in into a bird, and then the value becomes 1, or into the air, and then the value becomes 0. But this tells us then that there is something which can be called a continuum. So for defining a continuum, for working with the concept of continuum, you need, so to say, a certain threshold size to be above it. Otherwise, the definition of continuum is violated. And when you have a continuum defined, then funny things appear, like you have gas molecules, which are discrete elements, but when they are treated as a continuum, then you have new properties appearing, and that's pressure, for example, or viscosity, to say a few. And the same happens with the solid particles in a fluidized bed. There is the solids pressure, and then there is the solids viscosity also. Then coming back to the modeling in academia, we have the two types where you describe the solids by modeling each of the particle. Sometimes people don't trust me, my friends, when I tell them that there are people doing this, or computers doing this rather. But yes, this is possible. It takes time, of course. And then there are models describing the particulate phase as a continuum. So this is the Eulerian or Lagrangian-Eulerian modeling. Recently, in the last decade or so, there has been some kind of an intermediate approach, particle in cell, it is called, in which we have clusters of solids, which are considered as elements, but the cluster itself is a continuum. So that is also a new interesting approach. Anyway, coming back to resolutions, of course, the more to the right we go, the more resolved we are in length, in space and time, but the more time it takes on a computer to solve these problems. So this is the whole picture. And to this picture, in the last 20 years or so, we have added a new approach to modeling in which the momentum balances are dropped. And these are the ones that take most of the uncertainty, so to say, in the formulations and of the calculation time. So if we drop the momentum balances and limit ourselves to solve the mass and energy balances and use some expressions for velocities instead, because now the momentum balances are not solved, then we have something new, and this is called semi-empirical modeling. It's not empirical because we are caring about the mass and energy balances, but it's not CFD because we're not solving the momentum balances. This was perfectly summarized in my eyes by Miehanen and Hyppanen in this plot. We have the space and time scale, the resolution. So we have here the highest resolutions, DNS, direct number simulation, being the highest of them all. And here we have those correlation models or correlation expressions, 0, the typically steady state. And of course, they go here in a diagonal, as you said. And this new or this type of modeling that I was telling you about, the semi-empirical, can be found here then. So it's in between CFD and experimental correlations. We have been working with this for quite many years together with Valmet in developing biomass combustion. And this is what the model looks like, more or less. It is in the order of hundreds of thousands of cells, but this can be solved in 2 or 3 hours on a desktop computer. And this is one of the boilers that we have worked the most with. It is based in, or it is placed in the US. So here we have some results for it. This is the oxygen concentration field at the height of almost 20 meters. And there was an intensive measurement campaign, 48 points. And the model gave an average free error of 9%, which in the world of FV boilers is very good. Then we have also temperature measurements. This is the model, the simulated temperature field. And what you see here is that by the front wall, there are wing walls, heat extracting panels, and then you see these colder temperatures here. But in here, you have everything. Then you have the solids flow, the gas flow, you have the combustion, the reactions, you have the heat transfer, radiative, convective, and so on. And here, the average error was 8 kelvins for temperatures around 1100 kelvins. So again, it's we are very satisfied with the performance of the model. And of course, then we could calculate what is the heat flux to the walls for the water walls. Then this takes 2 or 3 hours to calculate the steady state. But if we use a one-dimensional modeling in the order of 10 cells, 10, 20, 30, then the calculation time gets down dramatically, of course, and then we can do funnier things, I would claim, like coupling, putting this fluidized bed reactor in a process, so coupling it with the steam side in the case of a heat and power plant. And this allows for transient simulations and how I want to see the interplay between the two of them. What is the response time of the reactor and what is the one of the steam side? And this has been leading to very interesting results. Typically, the assumption in literature has been that the reactor is very fast compared to the steam side, but we have seen that this is not a reasonable assumption, that you should account for both sides. And together with Karlstad Energy and Vik Energy, we have been modeling their boilers and some transients like this one, in which we change the load. And this is important because in the future, heat and power plants are envisioned to be slaves, so to say, of the system and of the renewables in the system, and to be forced to change in load rather fast and rather many times. Okay, this is how you model semi-empirical modeling. And I wanted to tell you finally about the loop, how we improve our models. We have model simulations and large-scale experiments. And you do this, you do your simulations compared to the experiments and then find something which you're not happy with. When you have identified that knowledge gap, what is creating this dissatisfaction, then with this knowledge gap, you plan targeted studies for that want to tackle that knowledge gap. You formulate theoretical hypotheses until you refine them until you are happy with this. Once you are happy with this, you have a new submodel that you put in the big model and the loop restarts. And this is a very good way to improve your model, which is typically the product that you have for industry or so. But also it is a very good way to identify where the activities in research should go here, because the model can tell you what is the weak link, the weak part of your knowledge, and then it can help you to design your research activities or strategy. And finally, if you make these targeted studies covering a wide operational window, then your model, you will compare it to measurements of a specific application, but your model will also become more and more generic, of course. And finally, I will talk about experimental techniques. And I will begin with fluid dynamic scaling. This is something that we've been working here at the division for many years, almost 3 decades, I would claim. So there is a strong tradition in this division. The whole principle is that there are scaling laws, and they consist of a set of dimensionless parameters. And if you respect them, if you keep them constant, the fluid dynamics will be preserved. This means that then you can measure in another unit. And afterwards, these measurements can be upscaled and tell you how the flow looks like in the hot, large-scale boiler then. We did this downscaling for a 200 megawatt boiler in Finland, a Valmet boiler, burning mainly biomass, sometimes even coal. And then with a scaling factor of 13, we built this in our lab. So we were not afraid of superstitions when we chose 13. There was some discussion on that. But as you can see, it's quite a large piece. The original boiler is 40 meters, so the lab one is 3 meters tall. And for comparison, here you have the tallest professor we could find in our division. We did, of course, the first thing we did was to, once we had built this, was to compare if the scaling was working or not. So we had these 4 reference cases, operational reference cases from Valmet, from the industry. Here is where our boilers mostly work. Check it out if it works or not. And we were extremely happy. As you can see, for the different cases, this is the high load with top concentrations of 10. And this is the lowest load with the top concentrations below 1. So a wide variety of operation. But for all of them, the experiments showed that the scaling worked very nicely. So why fluidodynamic scaling? Well, I would say there are a few advantages, but to me, the main 4 are these: increased operational flexibility. You cannot go to a fluidized bed boiler operator, a large scale one, a utility scale one, and tell it to do crazy things. But you can do crazy things in these fluidodynamical downscaled units in your lab in terms of flow and so on. They allow ambient conditions, and that means that you can use a wider range of diagnostic tools. You can have safer experimental campaigns, and not only safer, but also cheaper ones. So a lot of advantages here. I will focus on these, on the diagnostic tools and the ones that we have used. I will show 2 of them. So this is for studying the mixing of the fuel. We have magnetic particle tracking. And we have this from the Chalmers gasifier, in which with a camera probe, we look at, let's see. Probably like this. Oh, yeah. Let's see if this works. Yeah. So with a camera probe, after burning a few cameras, we managed to record the movement of the fuel, and then you can do digital image analysis of this and derive or extract a specific mixing rate for this situation. Instead, with magnetic particle tracking, you have a magnet, you encapsulate it to give it the right properties to resemble fuel on scale conditions. And then you can recreate the trajectory of this through the magnetic fields detected. Of course, this gives you then insight, a 3D insight into the flow, which you don't have from the camera. And from this, you can derive velocity fields, concentration fields, and so on, and even the viscosity of a bed. And this viscosity is something then that you would use in a generic formulation, of course. And then this takes you a step closer to a generic model for the mixing rate. And now I have a buffer slide, which I intended to walk you through if I had the time, but I don't, so I will jump it over. It's a pity. And I will talk about the other technique. How can we get good insight into the flow of fine solids? The magnetic technique that I showed you is good for large particles fuel because we need a magnet to track. But what about the very, very fine solids? As I said, we are very interested in knowing how they move, how they entrain from the bottom and so on. How they entrain from the bottom, how they go to the wall and so on. And we believe that we have found an answer in rudder. So rudder represents a big change in fluidized bed diagnostics. Typically, the techniques have been based on an integral principle. This can be radioactivity, this can be electric capacitance, but a signal is sent and then you measure in a receiver how the signal has been absorbed through a certain or along a certain path. So you have, for each measurement, some kind of average through that path. The rudder technique, instead, what it does is that the signal bounces back. So if you can have the response, all these bounces back resolved with time, then you know where in space these different bounces occur so that you can resolve along the path instead. It's a 1D against an integral method. So this gives a new paradigm, I would say, into the measurement or diagnostics of fluidized beds. Here we have the setup, and this is very, very fresh from the oven. I got these pictures a couple of weeks ago. So the rudder is sent into a mirror and then from the mirror into the bed. And this is how it looks like then, the signal. Still, we haven't processed data, but it looks like this. You see it's resolved and it fluctuates. So we are able to resolve both in time and space, the velocity field in this case. And this is, I would say, extremely promising. So I think this is mostly it. I walked you through these 3 sections that I announced, and just some claims to be done that developing fluidized bed applications can play a key role in the transition towards sustainable energy systems. That experience from major applications is valuable, but not directly exportable. One should be careful with this. And finally, that efficient development of new applications requires balance between mining of generic and specific knowledge. So thanks for listening, and thanks for co-working those who have done. Thank you very much.
So thank you very much, David, for this presentation. So now we'll go over and see if we have some questions. So we can see. So we can. So please, I will take up. So, is there any questions to David on this presentation? Yeah. Yes, we have one from us.
Yeah, Sayud.
Yeah, please.
Hello, thank you very much for your interesting presentation. As you know, for the fluidization technology for bubbling bed or circulating fluidized bed, it has been used for too many different types of fuel, solid fuels, just like coal or biomass. And recently I have even attended one lecture for you. It's on the using the biomass as neutral carbon fuel for CFB. But on the other hand, there is like new technologies for harvesting renewable energies. For instance, if we are talking about the solar energy, and we can use metallic powder like iron or aluminum or whatever, in such a way we can oxidize, which is equivalent to combustion, and after that there is reaction for reduction. My PhD was focused on the oxy-fuel combustion, and the idea came to my mind, why not to use the metallic powder for fluidized bed? From your point of view, do you think it would be visible for using metallic powder for either CFB or bubbling bed? Thanks.
Thank you so much. Well, you nailed it, because we are working specifically on that. When in terms of energy storage, we have been looking at the different solids that could be interesting. And we came to the conclusion that the calcium looping is one good candidate, but then we have metallic powders as good candidates too. And then we are working with that, and we're making the numbers, the economic numbers of that, and simulations with that. So I agree with you. I mean, it is definitely one of the strong candidates, and we work with it actually. So I'm happy to hear that other people have similar opinions, that these can be strong candidates for that.
Let's hope for joining forces.
Yeah,
definitely.
You. Thank you.
Thank you. So is there any more questions?
Yes. Hello, David. This is Irene.
Ah, hi.
How are you?
I'm fine. I will be better in a few minutes.
I got a question for you, David. What do you think about machine learning? When you were talking about so many experiments we have seen all over the years, all over the boilers, all over the gasifiers, wherever. And always we have had this problem of extrapolate, or how you said, export the results. How do you think it would be work, the machine learning tools for that?
We work a bit with that. We have a kind of expert in that knows more than I know, but I think it's a good tool, but it shouldn't be left alone, so to say. I mean, it's a very good tool and we must exploit it, but we must keep an eye on it because, I mean, it can give a lot of advantages and these digital twins and so on, but we should always be sure that, I mean, that the main laws, the main principles, the main balances are closed and the main laws are respected. And I think in that there is some, or I have heard at least that there is some challenge in that learning the machines that there are some rules in this world also. But yeah, I'm very interested in that, and we work with that in this work that I showed about transient simulations of power plants. So definitely a hot topic and something that interests us and that we want to work more with.
And if you allow me, I would like to ask you a second question.
Sure.
It is regarding the gasification. You know that my major has been always combustion, but now we are entering into gasification. And as much as I read, I always see the same problems everywhere. So why do the gasification have so many problems to be established as a consolidated technology? What do you think? Because I've seen the Chalmers gasifier a long time working. Why people is so reluctant to apply that?
Well, I would say, I mean, gasification has its problems, of course, and you could say tars and so on. But I think it's about the level of expectations. What do you expect it to have? I mean, technically, it works. The point I would say is what do you use it for? I think that is, I would say that is the main comment I could give. For example, we're working with BioShare in this retrofitting of boilers in order to turn them into poly generation units to gasify also. And of course, it's very straightforward if then you take this gas and you don't need to cool it down and you can burn it somewhere else close by, because then that's an easy case, so to say. But as soon as you need to cool it down or you need to refine it and so on, then of course there are costs related to that. And I think most often it's not about the technology, but it's about the cost or the cost of alternatives, so to say. But I mean, gasification is, I think it's a big or a very large, wild field, and it's difficult to put them all together in the same pack, so to say. I mean, I think there are different, depending on the feedstock, on the technology, there are different applications, and I wouldn't say that it's, so to say, that there has been a general failure for all of them.
Okay, thank you, David.
Thank you.
No, then I don't see any more questions. So then, thank you.
There are some questions in the chat, I think.
So question chat. Yeah, okay. Then we can find pointer.
If we can find it, yeah. Maybe not.
David, if you would like, I can assist by reading out the question. If you can find it.
We are close to finding it now. Thank you anyway for the invitation. Yes, now we see. Machine learning that we had already. And then Rahul Agarwal is, what is the definition of sustainable energy? What is sustainable today may not be in the future, such hydropower and the impact on aquatic environment. Yeah, well, yeah. Now, of course, environment is one part of sustainability, but usually one says that sustainability is wider than that. There is social sustainability, for example, also. So it is a very wide and a wide concept, so to say. And when I say sustainable energy systems, I want to apply that wide concept. Of course, the environment is one aspect of sustainability. The resources used is one aspect of sustainability. But I would like people to be aware that those are not the only ones. As I say, social sustainability, for example, is also important. So I think it's very, very wide. And as you say, I mean, any technology can be non-sustainable. There are no technologies that by definition are sustainable. I mean, even wind power, hydropower, solar power can be unsustainable also, depending on how they are implemented. So I agree. I mean, it's a good point, and something that we should bear in mind, that it's a wide field or a wide concept. Yeah. I think that's it.
Yeah. So then we don't see any more questions. So then, David, I will thank you very much for this very nice presentation. And I'm also very glad that we have come to this point. So my name is Henrik Thunman. I'm professor and the head of the division. So we've been working more or less together since you started here in different ways. And I've also seen very much how we've been developed during this time. And now we also see one part where you have very good credits in your education and your teaching, and you've been a master coordinator, which was not said here, for one of the master program, and now you are also responsible for the PhD education here at the department. So I see, I'm very happy that we come so far, and I also wish you very good luck in the future for the next steps. So then I will leave the word to Jan Petter. And then,
So I'll say also a few words to it, that I'm, I guess, very proud to see that we reached this point. I mean, I guess I was a little bit part in dragging you to Sweden. I hope you don't regret it too much. But so that was like 1998.
Yeah.
So that feels like both a long time ago and as yesterday. So. I think we had a lot of fun. Also, there was an EU project that we participated in from the very start, and you showed me some very nice part of Spain where I think it was our favorite meetings in that EU project, and also that we were more or less purely experimental, and you started this, as you mentioned, this semi-empirical, which I think has been quite a success. So really happy to see this, and as Henrik says, I really wish you the very best for the future. So
thank you so much. Thank you.
Okay.
Yeah. Okay. I heard it's my turn then.
Okay.
Just from your research group or former research group, I'm not fully part of it anymore, but it was a long time we spent together. The last 5 years, so we just have a small present. We're also extremely proud and really happy to have you see you go all this way. So thank you very much.
Thank you so much.
And just something really small from your group.
Thank you so much. Shall I open?
You can open now or
yes. Was almost Asian level on the packaging.
Yeah.
Yeah, so here's the group.
There, you can open this. It's like our small because we will of course also want to be part of the celebration. So we like to have some small party with you. You can decide if you want to take this present or not.
It's a dinner with the research group, and I here and now can say that of course I want to, definitely.
Great.
It'll be my pleasure.
The other one is more for your private pleasure than
okay.
Have discussed a little bit with Emma, so
good.
You can enjoy some evening with her.
That's very nice. Thank you so much. Thank you.
Congratulations.
Thank you so much. And maybe it's my time to say a few words also. And
because of course for everyone who has been around, it's clear that David has delivered a very interesting lecture. I think so. It was very, very interesting to get an insight into your field, and the way you presented it was very. I liked it a lot. I must say that. I also need to say a few things before I conclude. That is that today I have studied your CV in detail to see to kind of find out who is this guy. And I'd like to kind of see if there are some weaknesses, not to be because they are interesting in itself, but then that's room for improvements. And I have to say that I unfortunately I haven't found any weaknesses today. Everybody who listening should know that this there have been quite a few promotions during the year, but I've never seen anything as positive as we received from you. The chairman of ARCO called me and say that the ARCO committee was wanted to say they were proud of working at Chalmers at the place where one of our colleagues could receive evaluation at that level. So that needs to be said today. It was I felt proud also when hearing it. I think I speak for the entire management group of the department when I say that you are a very valuable and appreciated member of the management group. You do a fantastic job as a vice prefect for PhD education. And you have full top marks on all points which is necessary in order to become to be a solid worker at Chalmers. So who is this guy was my question I started the day with. And I would like to say I think you are a fantastic role model for everyone working at Chalmers, and that is my little gift to you. I will, of course, report back to the appointment committee that you have delivered a fantastic lecture and that we recommend Rector to approve you to appoint you to professor as soon as possible. Congratulations.
Thank you so much. Well, now my wife and my family will need to deal with my ego when I come home after this. Yes. So nice flowers. I'm expert in killing them, but this has been a very nice story. Since '98, I was telling Philip yesterday, it's been my half life almost. And I remember I came here as an Erasmus student. I should be here for a half year. And then Philip insisted that I should take a PhD a couple of times. And I said, never, ever. So I came back to Spain, had a couple of works, and then I realized, wow, Chalmers, that was really great working there. Both the tasks and the people and the philosophy at the working place was very nice. So I did my best to come back. I managed. In the end,
Jam down personal now to try to remember what.
Yeah. So yeah, since then I can say I have never regretted a single day. So it's been definitely the right decision. I would do it again 100 times. And it has to do with the task, but of course it has to do with the people that here. Weather, definitely. But yeah, it's yeah. I really enjoy it here. I'm thankful to everybody, the ones that give me confidence, the ones that give me joy every day coming to work. And yeah, it's a love story, I would say. Thank you.
So then I guess the transmission.
So then, thank you everybody to listen, and then to end for today.